Hi everybody, thank you for taking the course. If you made it this far, then you're done. Congratulations on the certification. This is the appendix section for the purposes of doing nominal hazard zone and maximum permissible energy calculations. So that's what I'm going to show you guys in this video. My name is Nate, I'm the author of the course. I worked as an optical engineer for about 10 years, and if you have any questions about how to do these calculations, I'm happy to do these calculations with you or for you, totally for free. Also happy to help you pick out any PPE, particularly laser safety goggles, that will work for your specific equipment, and answer any other application-specific questions you have, or take feedback about the course, or really anything like that. So again, thank you for taking the course. Hopefully it was of value to you, and hopefully it wasn't too tricky. Tried to make the questions and answers like learning style rather than just difficult for no reason. And hopefully you all stay safe while operating your lasers. So let's get started with MPE calculations. I'm going to share my screen and walk you guys through a few resources that will be linked as well in this module. All right, let's get started. So I have a bunch of tabs open. I'm going to link the important ones in the appendix here. Some of them are just referential that we'll talk through. So let's get started. So the first one is lasermpe.com. This is one of our buddies in the laser space, and if you're curious about the details of the physics behind MPE, this is a really great digestible resource for explaining how this works. So, as we talked about in the course, maximum permissible energy is basically the amount of light that your eye can absorb before it gets damaged. And so there's two units to keep in mind here. The first one is time in seconds, and the second one is the amount of light, which is measured in energy, and the unit for energy is joules. I actually used to get made fun of in physics class because I mispronounced this as jowls, because that was how it's spelled. But it is in fact joules. So this is different for continuous wave lasers and pulsed lasers, and I'm not going to run through too many of the details here, but if you're curious, this is a really great resource. And you can see that, like everything else with lasers, it's very wavelength dependent, right? So the maximum permissible energy for green light is much lower than UV. The reason for that is our eyes are very sensitive to green, so that we can track green vegetables for food, and our eyes are not very sensitive to UV because the sun is just blasting us with UV almost all the time. The other thing to keep in mind about UV in particular, I cannot stress this enough because it's the most common issue that I see, is that you have to have UV blocking glasses all the time. Like, even if it's a very dim amount of light coming from a UV source, it can give you cataracts so fast. I actually had to tell this to a dentist recently. Nobody had goggles. The dentist didn't believe me because they have an MD, but the technician did believe me, and he put on his glasses. So again, great resource for understanding some of the theory behind this, but let's talk about the calculation. So this is a laser hazard distance calculator. So there's three really important things to keep in mind here for calculating your nominal hazard distance. The first is the power of the laser, which is measured in milliwatts. So milliwatts is different than joules. Joules are a measure of energy, and watts are a measure of power. And there's a little bit of nuance in the physics behind that. The other one that you might not have seen before, the other unit, is milliradians. This is that MRAD. So it's like, holy smokes, what is a milliradian? I know divergence has something to do with angles. Why isn't this measured in degrees? Well, In physics, it makes things a lot simpler if you just put pi everywhere that you can, because the universe is very interesting like that. So 1 radian is equal to 180 degrees divided by pi. What the heck does that mean? It means that 1 radian is equal to about 57 degrees. And then 1 milliradian is 0.05 of a degree. So that's super weird. What is 1 degree? 1 degree is 17 milliradians. So you will never have to do this calculation yourself, because almost all lasers with a spec sheet are specified in milliradians. So just so that you're familiar with that unit of measure, it can be a little tricky if you've never seen it before. And then the third one is vision correction factor. I always just leave this at 1, unless there's some extraneous source. So what this calculator is going to tell us is the nominal hazard distance of a laser with a certain power and a certain divergence measured in meters. And meters are easy. A meter's about 3 feet. Everybody probably already knows that. So here's another one that we're going to use just to check our math. This one takes into account the aperture diameter. So that just means the size of the output. That does not mean the size of the spot, though. It means the size of the output. So what we're going to discover during this exercise is that if you have a fiber laser, the nominal hazard distance is super duper big, which means that you would have to be many, many football fields away to absorb the light in your eye without being injured. The implication of that physical fact is if you have a fiber laser, you need to have a curtain around it at all times, because the most common issue with high power lasers, which are almost always fiber lasers, is fiber breakage. And if that happens, the light can behave in really unpredictable ways. And there's a term for this in optical engineering called stray light or light leakage. And these are both really bad things because they're not measured and they're not controlled. So if you have a fiber laser, put a curtain around it. If you're building a custom setup where you have a known divergence angle, a known aperture angle, and a beam going through free space, you probably have a physics degree and already know how to do this, so have fun. But if you're working with industrial lasers or medical lasers or anything that's really high power class 4 with a fiber, you got to put a curtain around it almost always. So let's look at an example here. So this is an industrial welding fiber laser. So this does not include the welding head. That is, as far as I understand, application specific and interchangeable, and it's not worth doing the MPE calculations for the head of a welding laser welder, because the user should always have welding goggles on, and the welding area should always have an enclosure or be in its own room with an interlock or have curtains around it. But let's say you're moving one of these things, like this is a mobile one, and the fiber is still attached, and you roll it through a door and it busts the fiber out without you realizing. And then you go to turn it on, stray light everywhere. Oh my gosh, what do we do? So just so that we can understand which figures we need to take from the spec sheet to do this calculation, we need to understand just one more concept, and then we can use that to calculate the divergence angle. So here's our specs. So we have, in this family of lasers, we have the lowest power of 1,000 watts, the highest power of 6,000 watts. That's these guys. And we have our wavelength. Okay, that's great. So 1080, we know that's infrared. Really close to 1064, which is very common. And interesting thing about 1064, it is a 532 laser frequency doubled. You can Google that if you want to go down a really cool rabbit hole about crystal lasers. So Here's the important one. Laser beam quality BPP. And it's got these weird units. So we've got millimeters, which is a unit of length. Then we've got milliradians, which is a unit of angle. And then in parentheses, we have microns, or micrometers, depending on where you went to school, which is also a unit of length. So like, what the heck is all this? Well, we're going to find out. So I'm going to provide this link for you guys as well, but BPP, right, laser beam quality, is a measure of the output of the light. What is the quality of the output of the beam? Is it perfectly collimated? Is it focused down to a really small point? What is it doing inside the fiber? What is it doing outside of the fiber? All these things are critical. So you can kind of tell what all of these different symbols mean. So this is the beam waist, which is the thinnest part of the beam. So it's the radius of the thinnest part of the beam. And then the divergence angle, which is this Greek character theta, which looks like a 0 with a line through it. So here we go. We've got our center wavelength, 1080 nanometers. One note, when you're using this calculator, it's going to come defaulted with the units in there, just like it's shown here. Make sure you keep those if you're going to change the numbers here. So like, for example, if I want to bring this down to 5, I got to keep these millimeters and milliradians. So again, this is a very strange unit. Anytime you have two different units of measure together as a product of multiplication defining a spec, that means there's an equation behind it, right? And so what we're going to do here is we're going to take the nominal spec of 10 millimeters, put that in here as the beam parameter product, and then we have to figure out the beam waist. So we're going to make an assumption here. So this unit, what is this QBH? And why is it measured in UM? What is a UM? Well, it means micro, and it's a micrometer, which is, 1/1000th of a millimeter. So QBH, it took me forever to find a website that actually quotes out this acronym. It's a type of fiber. So okay, that gives us a clue. QBH, this is defining the spec of the fiber. So 300 micrometers is equal to 0.3 millimeters. If you guys ever run across a spec sheet that's super confusing, I'm happy to help decode it, just like we're doing here. So we're going to make an assumption here. If the fiber were to break, the output of the beam would have a waist, the smallest point, of 0.3 millimeters, which is the diameter of the fiber. And then based on that, we can calculate our divergence half angle. So, wait a minute. This says radius. This is diameter. So we need to cut that in half. And notice how crucial this beam waist is for the divergence angle. The smaller the beam waist is, the higher the divergence angle is. And it kind of makes sense. Like, the smaller this waist comes down to a point, the higher the angle is that you have to come in at, and vice versa. The higher the angle of the output, the smaller the beam waist is going to be. So we're going to go back to, oh wait, there's another figure in here that might be confusing. This m squared factor. What the heck is an m squared factor? Well, luckily for us, the good people at RP Photonics explain it super clearly. So an m squared factor is essentially a really quick way for laser designers to specify the quality of their beam. And it's defined by this equation here. And holy smokes, this is a lot of Greek. Like, just like the saying goes, you're speaking Greek to me. What does all this mean? So if you remember this little theta, the zero with a line through it, that's just your angle. And the great thing about physics is most of the Greek letters are standardized, at least in optics. So theta is almost always angle. Same with this one. This is like a fun looking backwards K. That's a lambda. And lambda always means wavelength. Now, not every spec sheet is going to call out these Greek letters. So again, if you ever have any confusion, I'm happy to walk through this math with you. Pi is pi, 3.14, and then the squiggly W is beam waist. So this is not super crucial to the calculation, but it can be interesting. So let's just go through the exercise. So we've got 1080. Our m squared factor is 29. Our beam parameter product is 10. Our beam waist is 0.15, right? Yep. And our divergence half angle. Great. So these numbers match. That's a good thing. So let's go through the exercise of calculating the nominal hazard distance from both of these calculators. So what is our power in milliwatts? So back to our spreadsheet. Our power is 1,000 watts. What is a milliwatt? It's 1/1000th of a watt. So we need to do 1,000, 1,000. So I've got 6 zeros in here. Holy smokes, that's a lot of milliwatts. 1,000 watts is insanely powerful. You do not want that fiber to break. Like I said, any of this crazy high class 4 stuff, it's got to be in an enclosure or a room or have really substantial curtains around it. And if you're doing installation, always defer to the manufacturer. But if you are in a hospital environment and you are borrowing equipment or, inheriting equipment or renting equipment and not all this stuff is clear, we can figure it out. So what is our divergence in milliradians? Well, according to our 2 calculations, our divergence is about 67 milliradians. We're going to round up just for worst case, 67 milliradians. And then just for fun, let's see how many degrees that is. 3 degrees. Pretty good. Almost collimated. And then our diameter at the aperture, that's going to be our broken fiber diameter, which is, again, 300 microns. And that's our diameter. Holy smokes, 168 meters. Yeah, that's way too big for really any building. You don't want this thing anywhere where it's going to be exposed. So let's go to our other calculator. So we've got 1,000, 1,000. Hopefully you guys can hear my clickety-clackety keyboard. And divergence angle, 67 milliradians. So if this is in the same order of magnitude, then we're good. I think the variable here is this vision correction factor. But yeah, 100 meters is way too big. Okay, so now, just to prove that we know what we're doing, let's go to a really small benchtop laser. So this is one of the lasers that we used in school at my optics college for testing. This is a helium neon red laser. It's a really small amount of power, 1.2 milliwatt. So these are great. They're $5,000, but they're really great scientific tools for alignment and testing and teaching college students how lasers work. Really great. So let's pull out our specs from here. So our output is 1.2 milliwatts, 1.2, and then our divergence. So our divergence here (1.4 milliradians). Great. Right? So our power level is really small, our divergence is really small. We should be in really good shape. And certainly so, we are. 5.5 meters nominal hazard distance. So this means that if you're in a normal sized room, you could be standing at the other side and get hit with stray light and you'd be totally fine. You would want to put your face right in front of it, but you know. And let's go back here and do the same thing. So we had 1.2 milliwatts, 1.4, and then let's take our beam aperture diameter. Beam diameter is 0.65. Great. Eight meters. So that's awesome. We know we're in roughly the same order of magnitude, 8 meters and 5.5 meters. So between these two calculators, you can safely assume that this laser is perfectly fine to have in a room propagating through free space, and no one's going to go blind. So the last thing that I'll cover for maximum permissible energy, if you're confident with reading plots and you know the wavelength of your laser, it's going to be pretty easy for you to calculate or to point out on the plot where you need to be safe. So like, for example, 400 to 700, which is the visible range, we have an incredibly low maximum permissible energy measured in joules per spot size, centimeter squared. And then the longer your pulse is, the safer you are. If you're incredibly short pulse, it's usually really, really high energy. And yeah, those pulses are just really strong. So you want to be careful about that. For CW lasers, you can see that the more time that goes on, the less safe you become. So that's an interesting trend of these plots to notice, is that CW lasers, continuous wave, are exactly what they sound like. The more light that hits you, the more light's going to be absorbed by your retina, the more in danger it is of being damaged. Pulsed lasers, usually really, really short pulses have really, really high energy. And so the longer the pulse is, the safer you are. Okay, in the last section, we're going to talk about how to read these plots for maximum permissible energy. If this is not something that is already super obvious to you or something that you were taught, you should really only be having to do these calculations if you're building custom setups. In almost all industrial, healthcare, and cosmetic applications, you're going to default to using the maximum personal protective equipment and enclosures around the lasers and all the control measures and good stuff that we talked about in the course. But if you're building custom setups and you need to classify a system, this is how you do that. So for continuous wave lasers, you can tell by the fact that this plot is trending down that the more light you absorb, the less safe you are, right? So if you're exposed for even just 1 second, you can only absorb 0.01 watts per centimeter squared, right? So that's a really tiny amount. That's 10 milliwatts per square centimeter. And most lasers are way more powerful than that because their spots are way smaller than a square centimeter. And then for pulsed lasers, we switch our units to joules because a watt is a joule per second. So for pulse lasers, the shorter the pulse is, the higher the energy is, given a fixed amount of wattage. So let's just go through the exercise of reading through this and interpreting the plot based on these instructions. So, for example, 5 milliwatt laser puts out 5 millijoules. If the spread of the beam is 1 square centimeter, just to make the math easy, the point can be found by looking at the column to the right, 1 second, and going up to the point 0.005. So that's about here. So if we draw a line across here, that represents our maximum permissible energy per wavelength. So already what you notice is that infrared is way over here, next to visible. So what that means is, for visible light, since our eyes are tuned to that, we can absorb a lot more exposure before we have damage. Whereas ultraviolet, which is way more energetic, shorter wavelength means higher energy. That's a way lower exposure time by 1 to the power of 10. So again, if you're familiar with logarithmic scales, it'd be super obvious how to read all these, but if you've never heard of E minus 12, this is 1 times 10 to the negative 12th power, if that makes any sense, saying that verbally. So here's what's interesting about spot size. So let's say all things being equal, if the laser was only half that diameter, we would have 4 times the amount of energy, 20 millijoules. So we're going to go here, and we're going to go to 0.02, which is about here. So we're going to go here and move 2 lines down to 0.0002 joules, which is about here. And what do we notice? So remember, our first line was around here. And then if we cut the beam in half, we move 2 orders of magnitude down in exposure time. So 1/100th the energy, 1/100th the time. So you can see how this is really spot size dependent as well, and pulse duration dependent. Okay, so this is the last plot that we'll go over. This one is quite a bit easier to interpret than the other two. So basically what we're seeing here is a functional equivalent of this plot, but with a different x-axis. So we're swapping time on the x-axis for wavelength on the x-axis, and now rather than wavelength being plotted, we have pulse duration being plotted. So each of these jagged lines represents a different pulse duration. So for example, if you have a 1 microsecond pulse duration, then we're going to be on this purple line, and let's say you have a wavelength of 600, then you know that your MPE is 1 e to the negative 6, which is about 1 microjoule per square centimeter. So again, the critical part of the calculation here has to do with the spot size, because it's not always obvious how to convert a spot size specified in millimeters to spot size in centimeters squared, because there's 2 exponents you have to deal with. So always happy to help walk through any of these calculations if questions come up. But yeah, this plot is a great resource if you know your pulse duration and your wavelength. Anyway, thank you. Hope some of that made sense to you. And again, always here to help with any questions that you have. And you're welcome to get a hold of me anytime to help sort through these calculations for your specific application or answer any general laser safety questions you might have. Thanks.